Concrete is one of the most frequently used construction materials in the world, noted for its strength, durability, and versatility. A concrete mix is a precisely blended mixture of cement, water, aggregates, and frequently admixtures to improve specific qualities. When these components are combined, they undergo a chemical reaction known as hydration, which causes the mixture to harden over time, forming a strong, durable substance. In this activity, we are going to compare the compressive strength of three different ratios, which is 0.3, 0.4, and 0.5 for cement paste and mortar. The water-cement ratio is a critical factor that influences both the strength and durability of concrete. Water plays a key role in the hydration process, where cement reacts with water to form the binding matrix that holds the aggregates together. However, the amount of water in the mix needs to be carefully controlled. We expect that different water-cement ratios will significantly affect the properties of the resulting concrete. A higher water content generally leads to a more fluid and workable mixture, which can be easier to place and shape. However, excessive water dilutes the cement paste, weakening the band between the particles. This results in a concrete with lower strength and reduced durability, as the increased water content leads to a more porous structure, making the concrete more susceptible to cracking, water penetration, and degradation over time. Conversely, a lower water-cement ratio is associated with higher strength because the cement paste is denser and more compact. This allows the concrete to achieve a stronger bond between the cement and the aggregate. However, reducing the water content too much can make the mixture less workable, which can lead to difficulties during placement and finishing. This may also introduce voids or improper compaction, which could negatively impact the longer-term performance and durability of the concrete. Hence, we anticipate that a higher water-cement ratio will result in weaker and less durable concrete, while a lower ratio will improve strength but potentially reduce workability, highlighting the need for a balance between these factors to achieve the desired performance. In the laboratory, testing of sample cylinders with varying water-cement ratios of 0.5, 0.4, and 0.3 were examined. For pure cement paste, the maximum load applied increased from 277.5 kN, 295 kN, to 337.3 kN, while the calculated maximum stress applied rose starting from 15.703 MPa, 16.694 MPa, to 19.87 MPa as the water-cement ratio decreased. Similarly, in the mortar samples, the maximum load applied increased from 255.5 kN, 267.6 kN, to 271.4 kN, and the calculated maximum stress applied increased from 14.458 MPa, 15.143 MPa, to 15.358 MPa as the water-cement ratio reduced. These findings emphasize the relationship between water-cement ratio and the mechanical properties of concrete, emphasizing the importance of mix design in achieving desired strength characteristics for specific applications. After conducting this activity, we've learned that achieving the desired properties of concrete, such as its strength, workability, and durability, relies heavily on precise measurement of careful mixing of cement, water, and aggregates. These components need to be combined in exact proportions to ensure that the concrete performs as expected in various construction applications. Among these factors, the water-cement ratio is particularly critical because it directly affects the concrete's internal structure. Too much water can weaken the mixture, leading to lower compressive strength and increased porosity, which makes the concrete more vulnerable to cracking and environmental degradation over time. Conversely, too little water can result to poor workability, making it harder to mix and place, and potentially leading to an uneven distribution of materials within the concrete. Therefore, finding the right balance is essential for creating a durable, long-lasting material that can withstand the stresses and demands of different construction environments, whether it be for infrastructures, commercial buildings, or residential foundations. Mastering this aspect of concrete mixing can lead to more reliable and cost-effective construction practices. After getting the results and gaining some knowledge from this activity, We want to know more about how other factors, such as the type of cement, type of aggregates, and curing conditions, influence the final properties of concrete. We also want to explore how the concrete behaves under different environmental stresses like varying temperatures or humidity levels. With this knowledge, we will be better equipped to apply the correct water-cement ratios and mixing procedures in future construction projects, ensuring that the concrete produced consistently meets the desired strength and durability requirements. By understanding how the water-cement ratio directly influences the concrete's compressive strength, workability, and resistance to cracking, we can tailor our mixing process to fit the specific demands of any project, whether it's a high-strength foundation or a more flexible structure that requires greater workability. This deeper understanding will also allow us to work on concrete mixtures for particular environmental conditions or structural needs. For instance, in environments with high humidity or temperature fluctuations, we can adjust the mix to enhance the resistance to weathering or thermal expansion.